Hi, I'm Sanjeev, and we are in the laser lab in Willis Annex. This is Joseph. Joseph, do you want to give an introduction and overview of your research?
Sure. So my name's Joseph, and I'm one of Tracy's PhD student. And my project mainly revolves around microbubble dynamics.
Cool. Why microbubbles? What's special about them?
Yeah. So to answer that question, I'll have to talk a little bit about the overview of my problem.
Yeah.
So kidneys are the organs in human body that helps cleanse and filter the blood.
Yeah.
But with the patients whose kidneys don't function normally, we have to take their blood outside of their body
Cool.
and then artificially cleanse it before transfusing it back to their body. This process is called hemodialysis, and because of this inherent nature of taking the blood outside of the body, there are ways for air bubbles to be introduced into the bloodstream. And as part of the safety measure, there is a device called an air trap that traps and prevents air bubbles from flowing into the patient.
Okay.
So yeah, that's where. There is an issue currently with this design because it uses buoyancy to capture the air bubbles.
Okay. Buoyancy as in art, so just let the bubbles float up. That's basically how
Yes,
it works.
it's pretty simple.
Okay.
So buoyancy will allow the bubbles to rise or float, and these conventional air traps will simply capture the bubbles using that. And physically, these buoyancies are only significant when air bubbles are large enough. So when it comes to smaller micro bubbles, these buoyancies are exponentially smaller, and it's almost negligible. And that's why micro bubbles cannot be filtered effectively using the conventional design.
Okay, cool. So then how are you trying to move bubbles, or how are you trying to manipulate these bubbles? What phenomenon are you trying to use?
Yeah, so my approach is experimental in nature. So overall, basically what I want to achieve through this PhD project is to come up with a better system or design or mechanism to capture the microbubbles.
Okay.
So it can only be effectively answered using an experimental approach.
Okay.
So essentially, in simple terms, I make bubbles, and I move the bubbles, and eventually I would like to remove these bubbles.
Make, move, remove.
Yes, exactly.
That's cool.
So yeah, in terms of making the bubbles, I'm using gas injection method, which seemed most appropriate for our particular case.
Okay.
And this method is simply, well, as its name implies, we inject gases to fluid.
Yeah.
So I guess I can explain that using schematics.
Yeah, if you could. So you mentioned make, move, remove. Could you take me through those steps?
Sure. So in terms of making the bubbles, we're using gas injection method.
Yeah.
Well, as its name implies, it's simply injecting the gas into fluid. So as you can see in the schematics, we have three main components. We have a micropipette, and we have a compressed air, and we have flowing liquid, which in this case we're using water. So the reason why we need a compressed air is obviously we need higher pressure to inject the gases through pipette, which has very high resistance. And also we need a flowing liquid because without it, the bubbles will simply grow at the tip of the micropipette. So we need additional force, in this case, drag force that comes from the flowing water to carry the bubbles off from the tip of the micropipette as they grow.
Yeah, okay, cool.
So that's how we are generating the bubbles.
Yep.
And here are some of the videos of our preliminary results. So this shows, about 220 microns of air bubbles being generated.
Yep.
And this is, using a smaller pipette, we could generate smaller microbubbles.
So almost a factor, a little smaller. Yeah,
factor of 10 even.
Factor of 10.
It is possible we could even make smaller bubbles.
Yeah.
So that's one of the problems that we're investigating. Yeah. And also, this is our latest result. So because of the many other things that we would like to test with microbubbles, we wanted the ability to generate one single bubble at a time.
Okay.
So using a new system, we were able to make bubbles on a demand. So one bubble at a time like this. So that's what we're also looking into. So that's basically all about making the bubbles.
Okay. And then
And once the bubbles are made, we have to move the bubbles because we want to eventually remove these bubbles.
so go on to the next step. Yeah.
Yes. So what I'm proposing is by using acoustic radiation force, we can remotely control the motion of the microbubbles.
Cool.
So acoustic radiation force is, well, it uses acoustic waves, so sound pressure waves, to remotely move or exert force on any object, such as bubbles. So using that, we can push the bubbles, and maybe by manipulating this mechanism, we might be able to effectively remove microbubbles.
Okay. Okay.
So in terms of physics, if you're interested.
Yeah.
Yeah, sure.
Go,
All right. So in terms of physics, so basically sound waves are pressure waves, which are sinusoidal.
Yeah.
So, and when those sound waves affect or drive air bubbles, by that I mean because of the sinusoidal pressure waves are affecting the bubbles will respond to it by oscillating its volume. So its volume will change, also sinusoidally. So those two sinusoidal effects, so driving force and its response in volume, can interact with each other, and that somehow results in resultant force that pushes the bubble in certain direction.
Okay, cool.
So
So right, that's very interesting. Yeah.
Yeah, that's what we're hoping to use to achieve the bubble removal.
And what's this?
So this is another preliminary video of our result. So just to prove the concept that acoustic radiation force can move the bubbles.
Yeah.
So as you can see, in the middle is a pipette, and this pipette is simply injecting the bubbles, and these bubbles are floating towards you out of the page.
Okay.
Or could be away from you.
Okay.
So as bubbles are floating, right now acoustic is off, but with the acoustic waves on, you can see the bubbles being pushed from the right to the left.
So it starts fading away, which means it's having an effect, yeah.
Exactly. So so this is basically a demonstration of how acoustic waves can be used to move bubbles selectively.
Cool, yeah. Well, that's very interesting. What does your setup look like? Like, that's very interesting in terms of the results, but how are you actually getting those results?
We have basically three main components in this experiment.
Yeah.
So in terms of making the bubbles, we have a compressed air coming from the pressure out the port. It comes through here, and this compressed air is filtered because we want to have clean, particle-free air source. So it's filtered through two filters, and this is a pressure regulator.
Yep.
So despite the pressures upstream, there can be some fluctuations because it's driven by compressor. This regulator will stabilize the pressure downstream, and we can also change the pressure levels.
Okay, that's really cool.
Yeah, so that's connected to a manifold where I can control the valves to open and close.
Okay.
And that's connected to a bubble generator. So that's where our micropipette and flow is located.
In some sort of bath with water, I
Exactly.
guess. Yeah.
So this is I'll call this an acoustic box.
Cool. Yeah.
So it will contain water.
Yeah.
And on the side you can see there is an acoustic window. It's essentially a membrane in the wall that I can attach an acoustic or ultrasonic transducer to effectively transmit the acoustic waves. That once the bubbles are generated, we'll be able to see the effect of the acoustic waves downstream within this acoustic box.
Okay. And like under your bath, there seems to be an opening. Is that how you're getting the recordings?
Exactly. Yeah. So because these micro bubbles are so small, they're not visible to our eyes, and also it's a dynamic phenomenon. So it's really hard to capture all the movements with obviously naked eyes or normal camera. So we need a microscope. So there's an optical access from below the acoustic box, and we also have a high-speed camera that can capture the dynamics of this phenomenon at a very high frame rate.
Right, that's really cool. Yeah, I guess when you're working with microns, you need all this.
Yes.
Okay, so you've said where these microbubbles come into effect, but in terms of just to give a bit of clinical background, what happens if microbubbles go into your body? What's the downside?
So yeah, what's so bad about
Yeah,
microbubbles?
essentially.
Right? Yeah. So air bubbles,
Yeah.
well, obviously they're not supposed to be in our body, but once they are introduced into our bloodstream, there are two main ways that they can cause harm.
Okay.
So the first and most obvious way is that these air bubbles can get stuck in small blood vessels,
Yeah.
and that can block blood flow, which will lead to ischemic injuries downstream from the blockage. So that's one way.
Yeah.
The other way is, so because air bubble is foreign to our body, once they're detected by our body,
Yeah.
our body will respond to them by inflammatory process. So our body will respond to it by inflammation, and that can also cause injury to the tissues.
Right. Yeah. It's very applicable, I guess, and important. But okay, so going forth from there, so you've got a lot of setup. What are the challenging aspects of this setup and your research, essentially?
Yeah. So, well, I think there's so many challenges, especially when you do research.
Yeah.
Well, I guess there are challenges at every step of the way. So
Okay.
the system itself is quite complicated. We have a water flow, we have a gas flow, we also have a microcontroller,
Yep.
and we have high-speed camera. So all of these to be integrated, it's not the easiest job.
It just doesn't happen.
Yeah, so that's a challenge.
Yeah.
But also there were challenges because even though we were able to simply use the publications that are available to make small microbubbles,
Yeah.
we couldn't use that because they used very high flow rates. So I've shown you a few videos previously. The first two videos, you could see that it only generated multiple bubbles continuously, and it required high flow rate because it depends on the drag force.
Yeah.
And that limits its applicability down the track with the acoustics.
Okay.
So the challenge for us was to improve this bubble generator so that we have better control and also the ability to make single bubble at a time.
Yeah.
So that
sure.
was one challenge, and we believe we are handling it.
Okay.
But yeah, it's in the process.
Okay.
And also the real challenge could be, so once all of this is achieved and we can move the bubbles, then the challenge is, how do we design or how do we manipulate this acoustic radiation force so that they're not just moved, but they're actually effectively removed from the blood flow, the fluid domain. So that's
one of the future work as well, is it?
Exactly.
Or what else can develop from your research?
Well, it seems like so there's a lot of things that we can do. So the first thing is after all this is answered, assuming that I'm able to achieve this new, better design of removing the bubble, the next question after that would be basically biocompatibility. Can this be achieved without damaging the blood? How safe is it? And if it does damage the blood, then what is the safe limit that we can use? What's the maximum acoustic intensity that we can use? Is there a safer way to apply the acoustic waves? So that's obviously one of the main future works that can branch out from this. Because we're dealing with water. We're dealing with the blood.
Actually.
And there's another example.
Go for it.
Clinicians undermine the effect of the microbubbles as opposed to larger air bubbles. The reason for that is microbubbles are very small, and because of that they have very high surface tension, and that helps these microbubbles to dissolve away relatively quickly. And there's a well-established theory behind this, and actually there's a formula that can be used to predict how fast they will dissolve. But the problem is this is all assuming it's pure water. But we are dealing with microbubbles in blood. And blood has, unlike water, a lot of components in them, one of which is fibrin. And
Yeah.
these fibrins can coat the microbubbles
Yeah.
and hence extend its residence time,
Yeah.
stabilize it. So, and there is no clear understanding on how this works,
Yeah.
how much the fibrins can extend its residence time. And obviously, once we can generate the bubbles in a very controlled way, we will be able to investigate this problem as well.
Oh, yeah.
This
that's-
will be another project.
Yeah, definitely, yeah, because I guess that's taking it to the next step from what you've got.